We have an example problem here. This picture is from our textbook, the Knight book from Pearson. The question is, what is the magnitude and direction of the force F on the 1 nanocoulomb charge in the figure? So we have these three positive charges at each tip of a triangle. The bottom two are 2 nanocoulombs, the top one is the 1. And that's the one we're trying to find the magnitude and direction of the force on. So we have Coulomb's law. Coulomb's law is the force on any one charge due to another charge, and specifically for point charges. So I can use this equation for finding the force on the 1 nanocoulomb charge due to this bottom left-hand charge. I'm going to call that charge 1. I know since these charges are both positive that they're going to repel each other. The only force I want to draw, though, is the force that the 1 nanocoulomb charge is experiencing. And since they're repelling, it's going to experience a force that points directly away from that charge. So this equation is going to allow us to find F1, which does have X and Y components. So the magnitude of the force, let's go ahead and calculate that. K, we know, is our constant. The two charges involved are the 2 nano and the 1 nanocoulombs. The distance between the two is the 1 centimeters, which we do want in meters. So again, the charge needs to be in coulombs, the distance in meters, because the units on K are Newton meters squared per coulomb squared. And so to get units of newtons, we have to have everything in those SI units. Okay, I'm going to keep this out a few digits. I'll round at the very end. The magnitude of this force, 1.798 times 10 to the negative 4 newtons. The magnitude, with the way I've drawn it over there on the picture, this actual vector is the one that has this magnitude. But this vector has X and Y components, which we can find because the angle in the triangle below down here is 60, which means this has to be 60 as well, because that force is pointing directly away from this bottom 2 nanocoulomb charge. Okay, so the X component will be this magnitude times the cosine of 60. The Y component will be the magnitude times the sine of 60. I'll do that in a minute. The 1 nanocoulomb charge, though, is also feeling a force from this other 2 nanocoulomb charge. Because they are both positively charged, they repel each other. I only need to draw the force on the 1 nanocoulomb charge because that's the charge I'm trying to answer in the question. What is the overall force on this specific charge? So I don't need to draw the forces or consider the forces on those 2 nanocoulomb charges, just the 1. Now, the magnitude of F2 is going to be the same. We have the same K value. The two charges involved are 2 nanocoulombs and 1 nanocoulomb. The distance is the same. So the magnitude of this force is going to be the same as the magnitude of the of F1 due to the other 2 nanocoulomb charge. The difference is that this F2 points to the left, so it has a negative x component, and it does point up as well. So the angle here is 60. The x component would be F2 cosine 60, but it's in the negative x direction. The x components are going to cancel. If you see that, you don't have to go through the steps of actually calculating those x components. The y components, though, are in the same direction. They're the same value and in the same direction. Right? This y component over here, I would say, is F2 sine 60, just like we saw with force 1. So the overall force on this 1 nanocoulomb charge is going to be F1y plus F2y. And that's because the x components canceled. But since F1 and F2 have the same magnitude and the same angle, the 60 degrees, we can just take 2 of either one times the sine of 60. So whether I have F1y or F2y here doesn't matter, because these oh, just kidding, sorry. Let me fix that. 2F1 or F2 times the sine of 60, because these y components are the same. So 2 times this magnitude times the sine of 60 is going to give us the overall magnitude of the force. So times 2 times the sine of 60. Now I want to round. So I have 2 sig figs given in the problem. So I will round this to 3.1 times 10 to the negative 4 newtons. This is the magnitude. The direction typically is an angle. We could say 90 degrees. Or towards the top of the page would be fine. Either way. So Coulomb's law works to find the electric force on a point charge due to another point charge, but it can only be used for one combination of charges at a time. So we just had to look at it twice and consider the force that each of those other 2 charges is applying, and then add them together. But again, vectors. We do have to remember our vectors.